Okay, problem set 27. This one is pretty much entirely finding area between curves, which is a new topic for us, but it's not too complicated. It's just a little bit tricky. There's a lot of room for little mistakes. So you want to be very careful when doing this, and generally you want to check your work as well, though I don't think that I'll be able to do that today, just because my wrist is not in its best shape. But let's go ahead and take a look at number 1. So we want to find the area of the shaded region on this graph when the C value equals 7. And the first thing I notice about this is that the area of the shaded region is the space between these two curves, right? So it stops at this point of intersection on both and goes right there. And it looks like, and we can see from their equations as well, that it should be symmetrical with respect to the y-axis. So it has symmetry across the y-axis, just like that. Which means that if we find the area of one half of this, say this one, because that'll be easier for us, then we can just double that, and that should be the area for the whole thing. Instead, you could find the area of both sides. Sorry if you can hear my dog jingling. You could find the area of both sides with two separate integrals, but we're just going to do the area of this side and then double that in this case. Mind you, that won't always work if a function isn't symmetrical, of course, but that's just something to keep in mind. So since this line here is y equals the absolute value of x, if we're only looking at it on this side, then I can consider it, for our purposes, y equals x, right? Because on this side we have no negative value, so that absolute value doesn't mean much. And I can see pretty clearly that it is our top function. It is on top of the other one, which means if I was to find the area of this top function, it would look something like that. So the area of the shaded region is going to be the area of this top function minus the area of this bottom function, which would be that area. You see how that leaves us with just this interior here. That's exactly what we want. So our top function is y equals x, and our bottom is that y equals x squared over c, and we know c to be 7. From here, it's just a matter of setting up that integral. So we first need to figure out, or we first see that they go up to this point c, which is 7. So it's going to be an integral from 0 to 7 because we're just evaluating this area here. And there's technically two ways I could write this. I could do the integral of this first function, so like this, and then subtract the integral of the second function. But based on our sum rules and whatnot with our integrals, I can actually combine those into a single integral. So I take the integral of the first function minus the second function. And doing it that way proves to be pretty useful for some more complicated integrals where you can kind of combine and cancel out any like terms that are present within the functions, just to make the integrals a little bit simpler. In this case, it doesn't change much. It's just less writing. So we're going to do this. So now it's just a matter of evaluating this integral. In this case, we just undo power rule for both of those, because remember this is just x squared times 1/7 basically. So this is going to turn into that. And then our other, it's going to be an x cubed, so it's going to get, divide by 3 over 7, and I can combine that to be x cubed over 21. And now we want to evaluate that along our bounds. First, plugging in our upper bound, we get 7 squared, which is 49, times 1/2. Then minus, and because 7 cubed is a large number, I believe it's 343, if I remember correctly, I actually noticed that my bottom number, my denominator there, has 7 in it. So I'm actually going to write out that 7 cubed, like so, just to make it a little bit easier, and I'm going to rewrite that 21 as 7 times 3. Now, we cancel out those 7s, and this turns into 7 times 7 divided by 3, or 49 divided by 3. And that's obviously a lot simpler to think about than 343 divided by 21, right? Just put it in lowest terms. Next, we have to subtract all of this with our lower bound plugged in. Luckily for us, though, if I plug in my lower bound here, it's a 0. Same here, which means we're just subtracting 0, which changes nothing. So now I've got this, and I think I'm going to turn these into mixed numbers to make that a little bit easier on myself. So it's going to be, let's see, 24.5 minus, and that should be 48 divided by 3 is 16, so it's going to be 16 and 1/3. Well, I know that 24 minus 16 is 8, so it's going to be 8.5 minus 1/3. I know 8.5 is 8 3/6. We're subtracting 2/6, so this area is 8 and 1/6 square units. But, and don't forget, that's just the area of this part here. We want the area of the entire shaded region, which is going to be double that. So it's actually going to be 16 and 2/6 or 16 and 1/3. On to number 2. This one's a little bit more complicated, just because we've got some trig functions in there, and I know those can be pretty confusing for a lot of us. But this is another instance of we want to find the area between two curves. In this case, we want to find the area between this function and the x-axis. So we don't actually have to consider any other curves there. Our second curve is technically our x-axis. But it's not just as simple as taking this integral and evaluating it. And the reason that is because this function, we need to check first if it ever dips below our x-axis. And if we're not sure why that is, let me kind of draw out an example for us. If I have maybe a sine function like this, if I find the area between these curves, I'm going to get this area here and this area here, right? I'm going to want to add those areas to find the area between the curves. But when I'm taking my integral, this area is going to be positive and this area is going to be negative. Because this is negative, it's going to actually subtract from that, and we're going to get an inaccurate reading of that actual space there. That's helpful for us sometimes, but in this case, it's not what we want. So whenever we find that it dips below the x-axis, we want to make sure that that integral is negative, so that we're dealing with positive areas only. So our first step is to figure out if we can find our zeros for this function, and let's take a look. So it's f of x equals cosine of x minus cosecant times cotangent. Remember that cosecant of x is the same as 1 over sine, and cotangent is the same as cosine over sine. So cosecant cotangent is just cosine over sine squared, which doesn't make this much easier for us. This is a bit tricky. I am going to rewrite this just a little bit, just so it's a little bit easier for us to think about exactly what we're looking at. Oops, sorry, this would be sine. And if I want to set this equal to 0, then, well, let's work from there. So let's try adding this to both sides. So we end up getting cosine of x equals cosine of x divided by sine squared. That's tricky. I'm trying to think if that's ever the case. And I'm not sure that it is. I could then multiply both sides by sine squared to get sine of x, cosine of x, or sorry, sine squared of x, cosine of x equals cosine of x, which again, I'm not sure ever happens. Let's think about our unit circle a little bit here. So that's, this is really difficult without a calculator, huh? Let me think this through. The easier route might actually be to sketch out this graph. Just because I'm not familiar enough with my trig rules and whatnot to really go from here, unfortunately. Let's think. If I plug in, if I plug in pi over 2, that makes this 0 and this 0. So both sides equal to 0. So this all is true when x is pi over 2, and also when it is 3 pi over 2. So we have a 0 at pi over 2, we have a 0 at 3 pi over 2. We don't actually ever go to 3 pi over 2, because remember this is our interval. So that pi over 2 is the only one that really matters. But it doesn't help us a whole lot. I wonder, is there anywhere else where this is the case? Let's try. Okay, so at pi over 6, I have, oops, it won't let me write there because of the stuff. Okay, and then pi over 4 is probably the only place I could see that maybe working. But I do want to check all of these just to be really thorough. Okay, so if we plug in a pi over 6, because that is a longer interval, if I plug in pi over 6, that's going to give me 1/2 squared, which is 1/4, times square root of 3 over 2 equals the square root of 3 over 2, which obviously is not true. So that is not a 0, or that's not a solution. If I plug in that pi over 4, that's going to be square root of 2 over 2 squared, which is then 2 over 4, which is 1/2, times square root of 2 over 2 equals square root of 2 over 2. That is also not true. So I don't see any other zeros, which means we just need to figure out, which means that probably along this interval, from the looks of it, our function is on one side of the x-axis. Now it's up to us to figure out if that is going to be positive or negative. We could go ahead and just kind of like sketch that out, maybe plug in a value to figure that out. But if the whole function is on one side, then that means that whole area is going to be either positive or negative, and it's not, we don't have to worry about any canceling. So we could actually from here just go ahead and take that integral. And that's exactly what I'm going to do. And if our answer is negative, then we just have to make it positive. Of course, this doesn't work if it's sometimes positive and sometimes negative. Then you would need to figure out on which intervals those are and split it up into two integrals. But luckily for us, it doesn't seem like that's the case here. So we want to take the integral of, this function. I know, of course, that the derivative of sine of x is cosine of x, so the integral of cosine is going to be sine. And if you remember our trig rules really well, I know that negative cosine of x cotangent of x is the derivative of cosecant of x, I believe. And that's going to be a positive cosecant, because when I take that derivative, it turns negative. And so now, remember, cosecant is the same as 1 over sine. So actually, I will rewrite that just so it's a little bit easier to think about. So it's sine of x plus 1 over sine of x from pi over 6 to pi over 2. And now we just evaluate. So we start off by plugging in the upper bound. So I'm going to get sine of pi over 2 is 1. Plus 1 over 1 is 1. Then we subtract our lower bound. So I'm going to subtract sine of pi over 6 is 1/2. And I'm still subtracting, so minus 1 over sine of pi over 6, that's 1 over 1/2, or just 2, which turns into a 2 minus 1/2 minus 2. Those cancel, which we just get a negative 1/2, which tells us it should, in reality, be positive 1/2. Next up, let's see. Okay, so our function equals this from 0 to 1. And we want to find the area between this function and the x-axis once again. So I see obviously that this is going to be below our x-axis, and that might not be obvious actually. I don't know why I said obviously, That might not be obvious just glancing at it, but I want us to stop and think for a moment, how could I rewrite this? Well, I have a negative exponent up here, so I could rewrite this as 2 over e to the power of x minus 2. If that x is a 0, well, then this is just 2 over 1, so it's 2 minus 2, which equals 0. If that x is anything greater than 0, and it must be within our interval, then this is 2 divided by something. And I know if that's maybe a 1, it's 2 divided by e, and e is like 2 point something. So this is going to be less than 2. Definitely. It's actually going to be less than 1 in that case, which makes this negative. Any point where this x value is greater than 0, this will be less than 2, making this whole thing negative, which tells us the entirety of this is under the x-axis on the interval provided, which means, once again, we can go ahead and take the integral, and this time we recognize that it's going to give us a negative area, so we just have to turn that positive. Which means from here, and actually on the homework, they probably won't accept us just putting it in like this, because that will be negative the whole time. What you'll have to do instead is go ahead and write that negative anyway, because that's the area we want. We're going to end up applying that negative at the end. We might as well do it at the beginning. And they want you to distribute that negative probably. So that's gonna turn this integral into a negative 2e to the negative x plus 2. And this is what we would write over here. So from 0 to 1, negative 2e to the negative x plus 2 dx. And then we, of course, need to take that integral. And we know our bounds are going to be from 0 to 1. Taking that integral, I know that this is just a coefficient. I know that the derivative of e to the negative x is going to be negative 1 e to the negative x. So going backwards, I'm going to divide by negative, so I'm going to get negative 2 divided by negative, so I'm going to get 2 e to the negative x. And of course, plus 2, it's going to be plus 2x. And of course, that's on our bounds from 0 to 1. We can go ahead and put that in over here. And now we have to just plug in those bounds and evaluate. So if I plug in a 1, that's going to be 2 times e to the negative 1, so it's going to be 2 over e, plus 2 times 1, which is just 2. And then we want to subtract plugging in our lower bound. So if I plug in 0, that's going to be 2 times e to the power of 0, which is just 2 times 1, because anything to the power of 0 is 1. So that's minus 2, plus 2 times 0, minus a plus 2 times 0, which is just 0. These cancel out, and our answer is just 2 over e. Which is a nice, pretty answer, luckily. On to number 4. This time we want to find the area between two curves on the provided interval. So once again, we're going to need to figure out which one is our top function and which one is our bottom function. And keep in mind that that might change at any given point. For example, if I have maybe functions that look like this, right? Finding the area between them on this interval, well, this top function, or this function here, I'll call that y, is going to be the top function for all of here, but it's going to be the bottom function for all of here because it comes on through like that. So at this point, I would need to switch to a second integral where I have different top and bottom, so I'm subtracting the other way. In this case, and I like to sketch out my graphs to help me, we want to do two things first. So we first want to set these equal to each other and find any intersection points, because where they intersect gives us an idea of where they would, that tells us exactly like the bounds of any integrals that we need to split it up into, right? So I'm going to set 2 over x equal to 2 over x cubed, and now we just solve for any intersection points. Probably the easiest thing to do here is just multiply both sides by each denominator. So I'm going to multiply that by x cubed, which cancels that out. And I'm just going to do that. So that's going to be then 2x cubed over x equals 2, or rather because the x cubed and that x cancel, it's going to be 2x squared equals 2. Divide both sides by 2, and I get x squared equals 1. So x equals plus or minus 1. Or plus or minus the square root of 1, which is just plus or minus 1. Which means that at either a positive or negative 1, these functions intersect. Negative 1 is not within our interval, so we can only include that positive 1. So we have an intersection point at x equals 1. We just kind of want to keep that in mind. So intersects at x equals 1. Now, let's just try sketching out this graph. So we know our bounds. I'm actually going to make that a little bit bigger so that it's easier to work with. We know our bounds are from 1/2 to 4, so I'm actually not going to include that negative bit there. Just going to do it like this. I'll say that's 4, 2, 1, 1/2, 1.5, 3. Of course, we don't have to plug in values for all of these. We're just going to get a general idea. Let's figure out about how high these go. So let's see, if I plug in 1/2 for that 2 over x, it's going to be 2 over 1/2, which is then just 2 times 2 because we're dividing by a fraction. So it's going to be 4. So I'm just going to make a note of that over here. F of 1/2 equals 4. And then, of course, we want to know that intersection point. So f of 1 equals 2. Same with g of 1, that also equals 2. Let's see what g of 1/2 equals. Well, 1/2 cubed is going to be 1/8. 2 divided by 1/8 is 2 times 8, which is 16. Which tells me we need to go a bit larger than 4 up here, right? And that's kind of what I'm looking for. I'm looking for those higher values that we want to keep in mind. Let's try let's try that endpoint f of 4. It's going to be 2 divided by 4, which is just 1/2. G of 4 is going to be 2 divided by 4 cubed. 4 cubed is 64. 2 divided by 64 is 1/32, which is pretty dang small. And that's actually probably all of the information that we need for this. So I'm going to go ahead and mark that as maybe a 20. 10, because remember, this is just a sketch. It doesn't really matter. Looks like we don't get any negative values down here at all. So it's just a sketch to get us a good idea of what this looks like. So f of 1/2 is 4. G of 1/2 is 16. That tells me a lot already. They both equal 2 at this point. And then from there, I probably should actually sketch this a little different so that we can get a clearer picture. It's always difficult to figure out exactly how this should be sketched. Why won't it undo that? Because I wanted to redo that line. Okay. So instead, actually, we're going to mark it like this because it never goes into the negative x nor y values. So these are the points that we really care about right now. And again, let's say we'll go up to, well, we'll just go up to 16 actually. Okay, so at 1/2, this was 4, and g was 16. At 1, they are both 2. Then this gets to be 1/2, but the other one gets to be much smaller. Oh, it's really hard to sketch to make that clear. So that's not quite accurate how I've just sketched that, but I do want that to be more obvious. So what's happening is something like this. It goes really, really teeny tiny. All the while our f of x goes something like this. And we see they cross over each other. So from this side, so up until this point 1 here, so from 1/2 to 1, our top function is g of x, and our bottom function is f of x. But from 1 on to the rest of the interval, our top function is f of x, and our bottom function is g of x. Sorry if this took me a really long time to kind of explain that. I probably should have color-coded that because it's still really hard to see. But going from there, that makes it pretty simple. We just have to take the appropriate integrals now. So that tells me that for my first integral, I go from 1/2 to 1, so up to the intersection point, and it's going to be g of x minus f of x. So it's going to be 2 over x cubed minus 2 over x. Okay, and that's my first integral. And then because we want the area between both curves along this entire interval here, we're going to add these integrals. So it's going to be 1 up to 4, and it's now going to be f of x minus g of x. So it's going to be 2 over x minus 2 over x cubed. And now we need to figure those out. I am going to erase this bit here because it's no longer needed, and we like to have that space, right? So going through this, remember that 2 over x cubed I could think of as 2 times x to the negative 3, to the negative third power, which then undoing that power rule, the integral of that would be x to the negative second divided by negative 2, so it's 2 divided by negative 2, which is just negative 1. So this first integral there, that's going to be negative x over x squared, negative 1 over x squared. I don't know why I thought, because this negative tells me it goes below, so it's negative 1 over x squared, minus, and then of course this is 2 times 1 over x. The integral of 1 over x is natural log. So that's that. And remember that that is on these bounds. And then we add the integral, the second one, which is just going to be kind of the opposite, right? So it's going to be a positive 2 natural log of x minus a negative this, so it's going to be plus 1 over x squared on these bounds. And now that we are done with those integrals bits, I'm going to erase that. Okay. And now it's just plugging in values and evaluating. Like then adding it all together. This is a little bit tricky just because of those natural logs, but it's not going to be too tough to work with. So let's go ahead and try plugging in our upper and bottom bounds for this here. So it's going to be negative 1 over 1 squared, so it's negative 1 minus 2 natural log of 1. And then, of course, minus all of this for our bottom bound, so it's going to be minus a negative, so it's plus 1 over 1/2 squared, so it's 1 over 1/4, or just 4. And then still subtracting a negative, so it's also plus 2 natural log of 1/2. Okay, and that's just for this first bit. Now we need to do the same thing over here. So plugging in that 4, it's going to be plus 2 natural log of 4 plus 1 over 4 squared, so 1 over 16, minus, now plugging in a 1 for all of that, so minus 2 natural log of 1 minus 1 over 1 squared, which is just 1. And now we combine like terms. So I see that I've got 2 negative natural logs of 1, so I'm gonna, and I see I've got 2 negative 1s, so I'm gonna combine that to be negative 2 minus 4 natural log of 1, and then I've got plus 4 plus 1/16, and then these natural logs here, and because I'm adding those, I've got to make myself confused. Remembering our log rules, so if I have 2 natural log of 1/2, this coefficient in front is the same as if I wrote this, if there's an exponent in there, which I'm going to use that to make it a little bit easier on myself so I can process this better, which is the same as natural log of 1/4. So it's going to be natural log of 1/4, and this is going to be natural log of 4 squared, which is 16. And then, of course, if I'm adding 2 natural logs, it's the same as multiplying their interiors. So it's natural log of 16 times 1/4, which is just 4. Okay. And that's it so far. let's see if we can further combine this. So I've got negative 2 plus 4 is just 2. So 2, and then I've still got that 1/16, so I'm going to say 2 and 1/16. And now I've got this. And I'm going to consider this to be a negative 4, so I'm going to rewrite that like so, remembering that that negative 4 can be my exponent, which would then be natural log of 1 over 1 to the 4th, which is still just natural log of 1, funnily enough. I believe I can do that. That should work. So then that's 2 and 1/16 plus natural log of 1 plus natural log of 4. So I'm now just multiplying these interiors, so it's just plus, well, so now it's just 2 and 1/16 plus natural log of 4. And I'm going to consider that done. If you want a specific numeric answer, you can plug that into your calculator to get that exact decimal. But I don't think it is a pretty one. I'm not sure if you need to do that for this homework. If you can put it in like this, I would recommend doing so. Just be really careful with formatting. But that is that. Let's take a look at our next question now. We've got number 5. So it says, write an integral to find the area of the region enclosed by these two functions on a graph, and then solve for that area. So this one's different because it doesn't give us a set interval. Instead, we are given two functions that enclose a specific area, and then presumably don't overlap again. So this will be best done probably by sketching this out. First, we're going to look for those intersection points once again, so I set them equal. To look for when they are equal, right, for when they intersect. Going to add x squared for both sides and subtract 4 from both sides. So that's going to give me 2x squared equals 9. So x squared equals 9 over 2. X equals plus or minus the square root of 9 halves. Or I could write that as plus or minus 3 over the square root of 2. So they intersect at those points. So I'm going to make a note of that. Remember, normally we would check to make sure that both of those points are within our interval, but this time we aren't given an interval. So we just have to deal with that. From there, I would like to go ahead and sketch it. You don't have to sketch it. You could just kind of see within like what points one is greater than the other and what points they're smaller. But I think that sketching it is a little bit easier to work with. I personally understand this better as of like visually for this topic, so I prefer to sketch it out. Know that 3 over square root of 2 is a little bit less than 3, but I believe it's definitely more than 1. I'm not sure if it's more than 2. It is. Okay, so it's between 2 and 3. So I can write 1, 2, 3, negative 1, negative 2, negative 3, and I'm going to put this as that point between 2 and 3. Oops. It's not exactly right because it's actually much closer to it's like there. But I'm just going to put that there so it's easier to read. This is a relatively inaccurate sketch, not perfectly to scale. Now I'm just going to plug in some simple values. So let's try plugging in 0. If I plug in 0 for that, so if I do f of 0, that equals 4. G of 0 equals 13. Okay. So these are going to go pretty high. I'm going to put that as maybe like 20 right now and hope that that's high enough. We might have to change that. I don't think we will though. If I plug in, so okay, should probably draw that out a little bit more. So I'm plugging in that 0, I've got 4 and 13. Plugging in f of 1, I'm going to get 1 plus 4, which is 5. plugging in g of 1, I'm going to get 13 minus 1, which is 12, which already starts to give us a picture of kind of what that intersecting area is going to look like, right? It's going to do something like that, and then we just need to take a look at the other side. Honestly, I think that's actually enough for us to figure it out. It's going to look something like that there, and I imagine it'll do something similar on the other side, but let's double check. So if I plug in f of negative 1, that's still going to be 1 plus 4, which is 5. If I plug in g of negative 1, that's still going to be 13 minus 1, which is 12. And yep, it just kind of mirrors and it encloses this area that kind of looks like an eye. So now I need to find the area of this, which we should be able to do with a single integral because it never goes below our x-axis, so we don't have any negative area. So, or sorry, that should be all the way over here. That's where that should be going. Not important though, because remember this isn't quite to scale. So our integral is going to be from each intersection point. So from negative 3 over square root of 2 to positive 3 over square root of 2. And now our top function looks to be g of x. So it's going to be g of x minus f of x, which is then, 13 minus x squared minus x squared plus 4. Distributing that minus becomes like that. And this is where I said that it's sometimes useful to combine those into one integral, because you see I've got a bunch of like terms that I can cancel out, which makes it just that much simpler for me to evaluate it here in a moment. Because now that is 13 minus 4, which is 9 minus 2x squared. And now I'm going to bring that down here. So I know the integral of 9 is going to be 9x. Now the integral of x squared is going to be 1/3 x cubed. So it's going to be negative 2 times 1/3 x cubed. And then we evaluate it on our bounds. And once we do this, we'll be done. Oh, right. So we already set up the integral, so I probably should actually write it over here, because that is part of the question. We set up the integral. We found that it was 9 minus 2x squared dx. Don't forget that dx. And now we are currently finding the answer. So if I plug this in here, it's going to be 9 times 3, so it's going to be 27 over the square root of 2 minus this cubed. Okay. So I'm going to, once again, I'm going to kind of write out that whole thing. So it's going to be 2/3 times this cubed, so it's going to be that 3 times. And we'll see why I do that here in a second. We see, first of all, that first 3 cancels, which turns this into a 2 times that times that times that. And we see, obviously, when I combine that, square root of 2 times the square root of 2 is just 2. So that turns into 3 over 2. The 2 cancels out. And now it's just 3 times 3 over square root of 2, which is just 9 over square root of 2. So I can simplify all that as 9 over square root of 2. And I can combine these into a single fraction. So it's 27 minus 9 all over square root of 2, which is just 18 over the square root of 2. Oh, that was fun. That simplified really nicely. Next, we have to subtract, plugging in our lower bound. So plugging that in, it's going to be negative 27 over square root of 2 for that first bit. And then, or sorry, yeah, negative. And then minus 2/3. And again, I'm going to write out that whole bit, even though we kind of see how it goes. Remember that this is negative, so it's going to be negative 3 over square root of 2 times negative 3 over square root of 2 times negative 3 over square root of 2. And now, once again, I see that cancels out, so it's 2 times negative 1 over square root of 2 times negative 3 over square root of 2. Combine this, and I see that becomes a positive 3 over 2. Still times that last one. The 2's cancel, Now that becomes a negative 9 over square root of 2. So it's minus a negative 9 over square root of 2, which turns into a plus. And once again, I can combine that, so that becomes interesting. Oh, yes, okay. I just saw something there that confused me for a second. So then if I have negative 27 over square root of 2 plus 9 over square root of 2, that's negative 27 plus 9 all over square root of 2, which is just like we did before, except now negative. It's negative 18 over square root of 2. But we are subtracting that, so it turns into, so it's a minus a negative, which is plus, which turns out to be 36 over square root of 2. And we can rationalize that. So it's going to be 36 square root of 2 over 2, or I could write that as 18 square root of 2. And that's our area. Okay. We've got, I think, 3 questions left. Let me double check. I think there's 12 questions total. Oh, we've got 6 questions left. Never mind. Okay, bear with me. I know this is a pretty long one. It's all pretty tedious. Let's take a look at number 6 now. Same deal, just different functions, right? So we first check for intersection points. So I'm going to set these equal. And I'm going to add x to both sides. So it's going to be x cubed plus 3x equals 9x squared. So it's going to be, if I then subtract 9x squared from both sides, I get this equals 0. And I'm going to factor out an x, make that a little easier on myself. And I want to believe that that factors nicely, but I don't think it does. And I'm frustrated by that. But we first see it, they intersect when x equals 0. So that's the first one. But then they also intersect whenever this part equals 0. So now I need to figure out when that is. That is the trickier bit. I want to believe that that factors, but I really don't think it does. So we're going to use quadratic formula. So x equals negative b plus or minus b squared minus 4ac over 2a. So that's 9 plus or minus the square root of 69, which is a little bit bigger than 8. I don't know exactly what that is. Damn, and I don't think that that can simplify any further. That's pretty ugly numbers. I don't like that. But we'll use them anyway. The one on the homework should not be this complicated. I believe it should factor out nicely. I should have come up with a better problem. So in this case, I will use the calculator for this, I think, just so that it's not unbearable. Actually, I want to see around where that falls. So if I do 9 plus square root of 69 divided by 2, that's about 8.65. If I do 9 minus square root of 69 divided by 2, that's, wow, that's a small decimal. Something like that. Okay. Sorry, my mom just called for me. Sorry about that. Going from there, so I want the regions enclosed between this point and this point, and then the region enclosed between this point and, oops, I just wrote that wrong, and this point. So in both of those cases, we need to figure out which function is on top and which one is on the bottom. I just erased half of that, didn't I? There we go. So in this case, let's figure out our top function and our bottom function. So this case, it's between, oh, nope, I wrote that wrong. It's between 0 and that. So from 0 up to that, and then from that up to the higher one. Okay, so that's somewhere in there. Something smaller than this, but that's between there, is maybe 1/4. So let's try plugging in 1/4. If I have f of 1/4, that's going to be 1/64 plus 1/2, which is then 33/64. And if I plug in g of 1/4, that's going to be 9 times 1/16 minus 1/4, which is then 9 minus 4/16, which is 5/16, or 20/64, which means that my g function is smaller than my f function, so my top one here is going to be f of x, my bottom is g of x. Now we want to find something in that other interval. And this is what I meant earlier when I said you don't have to sketch. For this one, I'm only not sketching because these are pretty ugly numbers to work with. Now for this interval, give me one moment. Now for this interval, we need to do the same thing, basically. So something in between here and here. Nice easy numbers, maybe 2. Could actually even just use 1. So then if I plug in f of 1, that's going to be 1 plus 2, which is 3. If I plug in g of 1, that's going to be 9 minus 1, which is 8. So my top function here is g of x, and my bottom function is f of x. And now we just have to do our integrals. So it's going to be 2 separate integrals, of course. So it's going to be first integrals from 0 up to here. And it's going to be f of x minus g of x. So it's going to be, I'm going to write it over here because I don't want to rewrite. So it's just going to be x cubed plus 2x minus 9x squared minus x. So that's going to be x cubed plus 3x, we combine like terms, minus 9x squared. Okay. And then our second integral is going to be from here. Oh my god, I keep writing that wrong. There we go, from here to here. I'm writing 64, but that should be 69. Wow, I've written a lot of them as 64. Goodness. Okay. Sorry about that. Oh my goodness, I almost did it again. You gotta be really careful about things like that. They really sneak up on you. Okay. Now this one is going to be g of x minus f of x. So that's going to be just kind of combining like terms in my head. Okay. Now from here we have to actually take those integrals and evaluate them on the bounds. Okay. Let's do this first one. I know that's going to be 1/4 x to the 4th. I'm going to jump here, so it's going to be minus 1/3, so 3, then plus 3/2 x squared from 0 to here, and then plus the second integral, which is then like so. From here. And for this one, I'm gonna be really frank, I don't want to do that, so I'm gonna plug that into a calculator. I hope that's not too troublesome. Just because they're such ugly numbers. Okay, so 9 minus the square root of 69 divided by 2, and then that to the 4th for this first bit, and then divided by 4. Okay. Then it's cubed times 3 okay, and then so ugly. Okay, then that's squared and times 3/2. Okay, and luckily then I plug in that lower bound of 0, and that's just all 0. So this first bit is something like this, which you can see why I didn't want to do it. That should be that's a 4. You can see why I didn't want to do that all written out, because wow, that's not fun. So then it's the other one, which is also not fun. So 9 plus the square root of 69 divided by 2. Okay. Okay. Sorry, it's so much to type. And it'd be so much worse to write, so I'm glad that I decided to do it in a calculator. Just to figure that bit out. So then plugging in that upper bound gets us something like this. Now we need to plug in that lower bound. Okay. Okay, and we're subtracting that. So we get not a much bigger number. It really just changes the decimals like after this point. Then we add all of that to this for our final answer of, whoops, didn't mean to do that, of roughly 429 and all of this. Okay. Next up is number 7, which is really no different from what we've been doing. It's just presented a little bit differently, so it might be a little confusing at first. Because this is y squared equals 10x and x squared equals 10y are our two functions that we want to find the area between. So I'm just going to turn them both into y equals equations. So if I have y squared equals 10x, well, that means y equals the square root, or sorry, plus or minus the square root of 10x. And then if x squared equals 10y, that means that y equals x squared divided by 10. So now these are the functions that we have instead. And frankly, I don't know that we need this plus or minus. It's an important habit to have, and it's good to remember it. I don't think for the homework that they care though, so I think that this is just okay. But just keep in mind that it is generally plus or minus. Okay, Now I want to find intersection points, so I want to set those equal to each other. Easiest thing to do here is square both sides. Oh, yes, and even if it was negative, that wouldn't change anything here. Squaring both sides makes that x to the 4th over 100. So then I can multiply that off, so it gets to be 1000x equals x to the 4th. Divide both sides by x. And 1000 equals x cubed, which tells me that x equals 10, just because I know that, right? So they intersect at x equals 10. Do they intersect anywhere else? Because we aren't given an interval, so there should be another point to consider, but I'm not seeing what that would be. I may have once again chosen a poor problem. But let's kind of test this out a little bit. Let's try and sketch it. So let's try, well, I'll call this y1 and y2, and I'll make this one red and this one blue. That rhymes, but in the opposite way. If I then do my y1, if I plug in 10, that's the square root of 100, which is 10. We'll say that 10 falls about there. Well, actually, we'll make it higher. Make it 10 and maybe 20. So 10 here. Oh, sorry, wrong color. 10 here. But they should intersect at that point, so they should actually both be there. And they do. If I plug in, well, tricky. I feel like I've made a mistake somewhere, but I might have just messed up on creating the problem. Anywho, for this question on the homework, you would find the points of intersection, ideally 2 or more, and then you would, figure out which one is the top and bottom function and do the integrals like we did in the couple questions prior. It's really no different aside from you have to turn them into y equals functions first. That's the only actual difference there. So I think I'm going to have to skip over this one because I'm not really sure how to remedy the issue that I came across there. Very sorry if you were really relying on that one, but I promise you, as long as you're able to turn those into y equals functions, it should be no different from the questions before. Let's jump to number 8. This time we want, so all 3 of these functions enclose a region. We want to determine that area. This is where sketching is really, really helpful, because we're going to sketch this big time. Okay. So first I'm going to see intersection points for the first 2 functions. So this is going to be y1, 2, and 3. So I'm going to check where those first 2 functions intersect. Going to add that to both sides. So I get 3x, and I'm going to subtract that from both sides. So 3x equals 3, which means that these 2 intersect at x equals 1. Now I'm going to check for intersections between y2 and y3. So it's going to be negative 2x plus 6 equals 3 minus x over 3, which I could also split up into 2 separate fractions, which I see just makes that 1 minus x over 3, which tells us pretty clearly it's y-intercept as well, which is going to help us for graphing. And now it's a matter of, well, I'm going to subtract 1 from both sides first. So it's going to be 2x plus 5 equals negative x over 3. And I'm going to multiply both sides by 3 just to get that out of the way. So negative 6x plus 15 equals negative x. Add that to both sides. I get negative 5x plus 15 equals 0, or negative 5x equals negative 15, or x equals 3. And now I want to check for any intersection points, or any points of intersection between the first function, so y1, and the third function, so y3. Okay, so it's going to be x plus 3 equals, and again, I can, oops, I believe that was at 3. And again, I can write this just like that. That's the same thing. So I'm going to do that here, since we already figured that out. Subtract 1 from both sides. X plus 2 equals negative x thirds. Again, multiplied by 3. Add x to both sides. 4x equals negative 6. X equals negative 3 halves. So that's just another intersection point. And now we can go ahead and sketch out our graph to see what area they enclose. So, goodness, it's deciding to be nice and slow. Okay. Goodness. Okay. So now I'm going to say, let's maybe go up to 5. Oh, we'll go up to 4 and maybe negative 4. Well, actually, I'll put that as negative 3 because it's a little bit closer in. Negative 2, negative 1, 1, 2, 3. That looks pretty even. Not the most even it could be, of course, but decent. Negative 3 halves is, of course, going to be right there because it's negative 1.5. And from here, let's go ahead and plug in some stuff. So I know that the y-intercept for that first function is 3. Y-intercept for that second one is 6. The y-intercept for this one is 1. Let's go maybe up to 10 then. Oops. Okay. That's pretty decent. So the y-intercept there is 3. Actually, I will color code these. So I'm going to color code, which will be a little bit difficult for me to keep track of, but that's okay. So y-intercept there. Next y-intercept is 6 and 1. Okay. Next, we know that y1 is just x plus 3, so it's just, it goes 1 for every x value. Oops. It just goes up and up and up just like that. And of course, down on this side. Just like that. Okay, I've got that first function graphed. Let's try the second one. It goes down, it's a negative 2x, so it's the slope of negative 2, which means it goes down 2 values for every 1 over we go, because of that rise over run, which means that going over 1, okay, that's where it intersects. That's good, we found that already. And then going down another brings us down to here, and then here, and then there, and so on. I think that's as much as we really need to do for that. Oh, if only I could draw a straight line. Goodness. Okay. And then our third function has a slope of negative 1/3. So for every 3 over it goes 1 down. So 3 over, and they intersect there. Okay. Then it looks something like that. That's just like that. Okay. So the area that they then enclose is, wow, that's ugly, never mind. It's all of this space in here. So I could just do that. And so now we have to figure out some integrals for this. Keep in mind these points of intersection. So that's 3, 0. That's 1, 4, I believe. Yep, 1, 4. And then that's negative 1.5, what is that value? So if it's negative 1.5 plus 3, it's going to be 1.5. Okay. Now I see that my top function changes at this point, but my bottom function is the same all throughout, which makes this nice and easy. So I'm going to split this into two integrals from this point. So first integral is going to be from here to here. My second integral is going to be from here to here. So this first integral is going to go from this point. So it's going to go from -3/2 all the way up to x equals 1. And my top function is going to be y1. My bottom function is going to be y3. So it's going to be y1 minus y3, which is that x plus 3 minus 1 minus that. So then let's combine like terms. That's going to be x plus x over 3 plus 2. And I can actually combine these. Just want a common denominator. So it's going to be 3x over 3 plus x over 3. So it's going to be 4x over 3 plus 2 is that first integral. Then my second integral is going to be from 1 all the way to 3, which is this last intersection point. So from 1 to 3. And our top function is going to be y2, so it's going to be y2 minus y3, y2. So it's going to be -2x plus 6. Again, minus 1 minus -x over 3. And again, we want to combine like terms, so that turns into 5. -2x could be -6x over 3. So it looks like that. Okay, and those are our integrals. Let's go ahead and evaluate them. Yep, we just have to find that area. Okay, so for this first one, that's going to be an x squared, so it's going to be 1/2 times that coefficient of 4/3 times x squared. So it's going to be, that's going to reduce to 2/3. And then plus 2x, of course, on these bounds. Then plus our next integral, so that's also going to be x squared. That's going to be 1/2 times -5/3, which is going to be -5/6 plus 5x from 1 to 3. And we plug in those bounds. Plug in a 1, I'm going to get 2/3 plus 2, and then plug in our lower bound. I'm subtracting 2/3 times 3/2 squared, or -3/2 squared, which is going to be positive. I'm just going to write this because see that that cancels and we're just left with that 3/2. And then minus a plus, but plugging in a negative, so it's going to end up being minus a negative, so it turns into a plus. 2's cancel. Okay. Now I plug in our bounds for this side. So plus 3 squared is 9. Or actually I could cancel out one of those 3's, so that's okay, so times 3, which turns into -5 times 3 over 2. So it's going to be -15 over 2 for our first bit, and then plus 15, and then minus, because we're plugging in our lower bound. This turns into a positive because it's minus negative. 1 times 5/6 and -5. Okay, now we just combine like terms from here. Let's see. So of course this is the same as 1/2. So that's 2 minus 1/2, which is just going to be 1/2. So it's going to be 2/3 plus 1/2 plus 3. And then that's going to be minus 7.5 plus 15, which is, that actually just turns out to be positive 7.5. Minus 5 plus 5/6. Okay. Which, if I combine those, that gets me to 8. We'll subtract a 5 and I get 3. Add a 3 and I get 6. So I'm done with all of those now. So now it's 6 plus, I'll call that 4/6 plus 5/6, which is then 6 plus, a lot of 6's. 6 plus 9/6, which is then just 7.5. And that is our area. 7.5 square units. Our last 4 questions, looks like, are just taking the integral. It's not even worrying about areas between functions, but it looks like we might have to use some U-substitution for one of these. And I think we'll use U-substitution for this one here, and I'm trying to figure out what my U value should be. And like I said, it's not always easy to tell what our U value should be right away, so we end up fiddling with it a little bit, playing around with a few different U values. I'm going to make U equal to the inside of that square root for now, and see how that works for me. Then, of course, the derivative of 9 plus e to the t is just e to the t. But I need e to the 3t, which would be e to the t to the power of 3. Or e to the t times e to the t times e to the t. I see probably the easiest way to do that is to get some e to the t value. So I'm going to subtract 9 from both sides. That gets me u minus 9 equals e to the t, which is helpful because now I can multiply this to this 2 more times to get that e to the t times e to the t times e to the t, which means I have to multiply this times this twice. So that gets me u minus 9 du equals e to the t times e to the t, or I could write that as e to the power of 2t. And now I'm going to do it again so that we get that e to the 3t. So I'm going to u minus 9 du equals e to the 3t dt. And now I've got a u value for in there, and I've got my du and whatnot to substitute there. So I can go ahead and do that. I am, however, going to distribute that first. So I'm going to go ahead and do u minus 9 squared, just because I think that that'll be a little easier to work with. Okay, so it looks like this, which is the same thing as all that, right? I've just distributed that out. So now, instead of this, I can plug in a u here, and I can plug in all of this here. So it gets to be the integral of u squared minus 18u plus 81, and then times the square root of u, which I could then write as u to the 1/2 du. And that might still look like it's not something we can really work with, but all we have to do from here is distribute again. Because I can distribute that 1/2 because we're just multiplying, right? So u to the 1/2 times u squared. When we multiply exponents with the same base, we add those exponents. So it's going to be u to the power of 2.5. Or I could write that as u to the power of 5/2, which I will do. Then this is u to the power of 1. So that's going to be u to the 3/2. And then plus 81 u to the 1/2. And now we just undo that power rule. So I'm taking that integral, I'm going to go backwards. So it's going to be u to the 7/2, and then I divide by this. Okay. Same here, so it's going to be u to the 5/2, and then I divide by that, so I'm going to get 2/5 times 18, which is 36/5, which is an improper fraction, but I'm going to leave it alone right now. And I'm going to get u to the 3/2, and then it's going to be 2/3 times 81. I know 81 is the same as 27 times 3, so I am actually going to cancel that, so it's just 2 times 27, so that's 54. And then don't forget our plus c, because this was an indefinite integral. And that's all we have for that one. That's our answer. So let me erase that. And so our answer is like so. Now, just got a few more problems. Again, I'm really sorry that this one takes so long. This homework is very tedious. This next one might look confusing just because well, these are multiplied, but all we have to do is distribute. It's that simple. So I take 5x plus 2 times 5x minus 2, and I know that's a perfect difference of squares, so that's going to be 25x squared minus 4. And feel free to double check that by distributing that out, but it should be this. So then I could rewrite that, and this is a definite integral, so don't forget those bounds. And from there, we just undo that power rule. So it's going to be 25 thirds x cubed minus 4x from -1 to 1. Keep plugging in, or not keep plugging, but plug in those bounds. So I'm going to get 1, oops, why did it do that? Okay, so it's going to be 1 cubed, which is just 1, so it's 25 thirds minus 4. Minus, plug in a -1, which is going to be plus a negative, or minus a negative, which turns it into a plus. And then minus a negative, but plug in a negative. So that turns in, that's just like this, I believe. Hold on. So we're subtracting a -4x, where x is -1. So we're subtracting a positive 4. Yep, okay. Now combine like terms, and I've got 50 thirds minus 8. Let's see, 50 thirds is 16 2/3. Minus 8 is just 8 2/3. So I can just put that as our final answer there. 8 2/3. This next integral is really easy. It just looks confusing because of those natural logs and the e to the x. But remember, derivative of e to the x is just e to the x, which also means our integral of e to the x is just e to the x. Because this is just e to the x, it makes it really, really easy for us to work with. So my integral is just going to be e to the x evaluated on these bounds, which is then e to the power of natural log of 12 minus e to the power of natural log of 2, which those natural logs and the e's cancel out, so it's just 12 minus 2, or 10. And then finally, this one is that fundamental theorem of calculus. So let's see how well I remember it. So if our function is equal to this integral, then the derivative of this function, well, it cancels out the integral sign, but we still need to evaluate it on these bounds. And remember, we also multiply by the derivative of each bound. So let me just rewrite out that fundamental theorem of calculus. So if I have maybe h of x and g of x as my bounds, and I've got a function f of x inside here, then the derivative of this function is going to be f of h of x times the derivative of h of x minus f of g of x times the derivative of g of x. So that's all we have to do here. So we're going to plug in that upper bound first, so it's going to be 2 minus x cubed to the 4th, which is x to the 12th, all to the 1/6, times the derivative of x cubed, which is 3x squared, then minus, plugging in that x squared, so it's going to be 2 minus x squared to the 4th, which is x to the 8th, to 1/6, times the derivative of x squared, which is 2x. And that's quite literally it. That's all that we need to do here. And boom, there's our answer. And yeah, we don't need a plus c because we aren't taking that integral, we're taking the derivative of an integral, so that constant would disappear anyway. And that's it for this homework. So it was quite a bit. I know, I really recommend sketching things out like this. But yeah, I hope that this video was helpful. And good luck to everybody on our upcoming exam this week. Thank you for watching.